course. I'm the lecturer of this course, Zhang Dong. This course is LTE Basic Principles. Let's see the contents of this course. This course we will study three parts. The first part is LTE overview. The second part is LTE network architecture. The third part is LTE protocols and frame structure. Okay, let's see the first part, LTE overview. Before we learn the LTE, we should know the LTE background. And in LTE background, we should know two concepts. The first concept is 3GPP. 3GPP means the third generation partnership project. This is one organization of standard. So if you want to check any standard of LTE, you can visit 3GPP website. Okay, and the second is LTE. LTE means long-term evolution. So LTE is the UMTS long-term evolution standard series developed by the 3GPP. Okay, so this is the meaning of 3GPP and LTE. And then we can see the evolution path of the mobile communications technology. From this slide, we can find three paths. The first path is from GSM to 4G. The second path is from CDMA to 4G. The last path is from 802.16 to 4G. And we are familiar about the first path from GSM to 4G. Okay, and as we know, GSM is the second generation, and the GSM only can provide voice services and just can provide some basic data services. Okay, so we want to provide voice services, we upgrade our system to GPIS, and the GPIS is only for data services. So we can say GSM is only for CS. CS means voice, it's circuit switch, and the GPIS is only for data, so it's a PS. But the data rate of GPIS is slow. The maximum data rate of GPIS is 171.2 kbps. After that is Edge. Edge we can also say is enhanced GPIS. An Edge can provide 384 kbps in maximum. Okay, so GSM, GPIS, and Edge, they are all in the second generation. And GSM is 2G, GPIS is 2.5G, and Edge is 2.75G. Okay, after that, we're going to 3G. And 3G, we have TD as CDMA, WCDMA, and CDM2000. They all belong to 3G system. Okay, we are familiar about the WCDMA, and the WCDMA is 3G, and 3GPP also defined R99 of WCDMA. R99 means the release of 1999. And the WCDMA compared with 2G, the data rate increased because the bandwidth of WCDMA is wider than 2G. As we know, in 2G, the bandwidth of one carrier is 200 kHz, but in 3G, the carrier bandwidth is 5 MHz. Okay, so because of wide bandwidth, so the data rate of WCDMA is much higher than 2G, and the maximum data rate of WCDMA is 2 Mbps in downlink. After that is HSDPA, HSUPA, and HSPA+. HSDPA is enhanced for downlink, HSUPA is enhanced for uplink, and HSPA+ we can also name enhanced HSDPA. So in different systems, the data rate also increased. For example, in HSDPA, the maximum data rate is 14.4 Mbps, and HSUPA is 5.76 Mbps in uplink, and HSPA+ the maximum data rate can be 21.6 Mbps in one carrier. Okay, so this is a 3G system, and they are all using CDMA technology. After that, we are going to LTE. And here, please pay attention. LTE is not 4G. LTE is a 3.9G. And LTE has two different modes. There has a FDD mode and a TDD mode. So we have FDD LTE and TDD LTE. Okay, after that is 4G. So what is 4G? 4G actually is LTE A. Okay, so LTE is real 4G and LTE is 3.9G. So this please pay attention. So this is the first pass from GSM to 4G. And the second pass is the CDMA system. CDMA system is widely used in some North American countries. Okay. And the third pass is from 802.16d to 4G. What's this? Actually, this is WiMAX. Okay, this is WiMAX. But WiMAX is only has TDD system. But LTE we have FDD and TDD. Okay, so this is the evolution path of the mobile communication technology. And next we can see the objectives of LTE. That means if we want to realize LTE, which value and which object we should satisfy. Okay, we can see one by one. First, the peak rate of LTE in downlink should be 150 Mbps and uplink should be 75 Mbps. 75 Mbps. And we can see here the downlink maximum data rate is 150 Mbps. That means we are using 20 MHz bandwidth and 64 core modulation and all the resource to one user. And then we can get this value. And this value is just on paper. Okay, just on paper. It's not a real data rate. This is the peak data rate. But we can see the uplink peak data rate is the half of downlink, right? Because we know in downlink we are using OFDMA technology, but in LTE uplink we cannot use OFDMA technology. In uplink we use SC-FDMA technology. SC-FDMA means single carrier FDMA. Why we cannot use OFDMA in uplink? Because in uplink we don't want has a higher PAPR, right? So we want to lower the PAPR, but OFDMA has a higher PAPR, so this is not good for the terminals. So in uplink, we are using the single carrier PAPR, a single carrier FDMA, and a single carrier FDMA it can lower the PAPR. PAPR means the peak average power ratio. Okay, so this first is the peak rate. The second object is low latency, and here has CP and UP. CP means control plane, UP means user plane. So control plane you can think just like signaling, and user plane just like traffic. So in LTE system, control plane delay is 100 milliseconds, and user plane delay is 5 milliseconds. How to understand these two latency? In control plane, 100 milliseconds, you can think just like when your terminals, your LTE terminals from idle mode switch to connected mode. Okay, from idle mode through the switch to connected mode, the mode change. This time it needs 100 milliseconds. Okay, 100 milliseconds. From idle mode to connected mode, we need 100 milliseconds. Of course, from idle mode to connected mode, they need to transmit several signalings. Okay, and the second is the user plane, is the traffic. Traffic, that means your terminals has already in connecting mode, and now your terminal will send an IP package, and this IP package is empty IP package to the network. After that, the network will give you a feedback, right? So this latency is 5 milliseconds. And we can see this 5 milliseconds are also the same, just like one cell, only one user. In this way, your latency can be 5 milliseconds. And we know if the user increase and also if your service change, this latency, it will be increased. So you can see this is what? This is the uh, smallest the latency. Okay. And the next is lower capex and opex. And the capex we can say is a construction cost, and opex is a operation cost. Why LTE has a lower capex and opex? Because LTE network compared with 2G and 3G network, we removed RNC and BAC. So that means in LTE wireless part, we only have base station, right? We only site, not like 2G and 3G, we have site and base station controller. Of course, we no need the base station controller operation, and also we no need to buy the base station controller. So LTE network has a lower capex and opex. The next is a spectrum flexibility. As we know, in 2G and 3G, our spectrum is fixed, right? Just like 2G, 1 TRX is 200 kHz. And in 3G, in WCDMA, no matter WCDMA, HSDPA, and HSDPA Plus, the carrier bandwidth, they're all 5 MHz. But in LTE network, the carrier bandwidth can be flexible. And in LTE, we can provide 1.4 MHz, 3 MHz, 5 MHz, 10 MHz, 15 MHz, and 20 MHz. So different country or different operator, we can select different bandwidth, because we know in some country, just like some small country, and this country only just like one island. So they just uh, they just select 3 meg or 5 meg, right? And also maybe some operator are private operator, so they just select 3 and 5. Okay, but of course the bandwidth whether means the throughput and the capacity, it will be higher. Okay, so this is spectrum flexibility. The next is higher spectrum efficiency. So what is spectrum efficiency? And this means we can use your maximal data rate divide your bandwidth. The result is spectrum efficiency. For example, in LTE, the maximal data rate is 100 meg bps, right? And we divide your bandwidth is 20 megahertz, right? So this result is what? Is a 7.5 bit per hertz per second, right? So this is LTE spectrum efficiency. That means 1 hertz in 1 second can support 7.5 bits. So we can compare with the 3G. 3G, this value is lower than LTE. So that's why we said LTE has a higher spectrum efficiency. Okay, the last is a better coverage. Why? Because in LTE we have some new technology. For example, MIMO technology, right? MIMO technology. MIMO is a multiple input and multiple output technology. And also we have beamforming technology. Okay, BF, beamforming technology. Those technology can also improve the coverage. Okay, so this is the objectives of LTE. That means if you want to deploy LTE network, these 6 objectives, they all need to satisfy. Okay, so this is the objectives of LTE. And then let's see the second part of this course is LTE network architecture. See, this is the LTE network architecture. LTE system totally we named EPS. EPS means Involved Packet System. And EPS will divide into EPC and EUTRAN. EUTRAN is LTE wireless part, and EPC is LTE core network. And EUTRAN is easy because in EUTRAN only one node, this node named E node B, only site. But this E node B function just like node B plus RNC function together, because in LTE wireless part we removed RNC. Okay, and in core network we named EPC. EPC means Involved Packet Core. Okay, packet core. So please pay attention. This is packet core. Packet core, that means LTE core network only support PS, cannot support CS. So that means LTE network cannot provide CS voice, only can provide PS voice. For example, like VoLTE, VoLTE. If you want to support CS, okay, please fall back to 2G and 3G network. And then between different nodes, there has an interface. For example, between E node B, the interface is X2 interface. And between E node B to core network, and we know E node B can connect to MME and SGW in core network. MME is for the control plane. SGW is for the user plane. So no matter MME and SGW, this interface is named S1 interface. So S1 interface is connected between E node B and MME and SGW. Okay, so this is a LTE network architecture. We can find LTE network architecture is much more simple than 2G and 3G network. And this is the network architecture in logic. Okay, and here EUTRAN, the same like a previous slide, this is E node B, right? And this is MME and SGW. Okay, so they are all S1 interface, but in logic we are divided. So the first is S1 to MME, second is S1 to U. U means user plane, because now SGW is responsible for the user plane. And others is core network. Okay, core network. In LTE core network, beside MME and SGW, we also have PGW, PCIF, and HSS. HSS is home subscriber system. You can think HSS just like the HAR in 2G and 3G network. And the PGW is used to connect to the internal network and external network. For example, here can connect to the internet. And also, if we want to support voice over LTE, so the PGW also need to connect to the IMS. Okay, because IMS is used for voice over IP. And also for LTE network, also has interface to 2G and 3G core network, right? GRAN is 2G and UTRAN is 3G. Why? Because in some case we need to provide our voice by 2G and 3G network, right? For example, like a CS fallback. So if you want to do the CS fallback, okay, we need interface between 2G core network, 2G 3G core network to LTE core network. Okay, so this is the LTE network architecture in logic, and the previous slide is LTE network architecture in physical. Okay, so this is the second part. Now let's see the third part is LTE protocols and frame structure. Okay, this is LTE and SAE protocol structure. LTE you can think just like wireless, and SAE you can think just like core network. So that means this protocol is between wireless to core network. Okay, we can see this picture. They have the three parts. The first part is UE, second part is E0B, the third part is core network, include MME and SGW. And here you can find they have the two lines. Green lines and the red lines. The green line is signaling stream and the red line is data stream. So signaling stream you can think just like control plane, and the data stream just like user plane. Okay, we can see the user plane first. User plane first. This just like if one UE want to do some data services, how to process in the protocol. Okay, how to process in the protocol. Okay, we can see here in UE part, the first is app, right? This app means application, just like what kind of data services, what kind of application you want to do. For example, I want to listen music, I want to downloading, I want to watch video. So this is app. After that, we are going to the next layer, okay, PDCP layer. Because in LTE network, because in the protocol, they don't care about your voice, your video, your music. They think you're all the same. They're all IP package, right? So all the different application going to the PDCP. PDCP only can find IP package. And what is PDCP? PDCP means Packet Data Convergence Protocol. And the PDCP in here has two functions. The first function is IP head compression. The second function is encryption. IP head compression, that means because now we want to transmit our IP package in wireless interface, right? And we know the radio interface resource is less than fixed network. You know, in LTE, here the bandwidth is only 20 megahertz. So we want to save our resource. So before we transmit our IP package, we will do the IP head compression. So that means we will reduce the IP head size. That means after the IP head size reduced, we have more resource can transmit your data. And the second is encryption. The same, the radio interface is open interface. We want to protect our information, so we need to encrypt. Okay, encrypt. Okay, so this is the function of PDCP. After PDCP, we are going to the next layer is RLC. RLC is radio link control. Radio link control. Okay, this layer has three functions. The first function is classification. The second function is recombination. The third function is subsection. Okay, this is the three functions of RLC. And RLC also has three different working mode. The first mode is AM. Second mode is UM. The third mode is TM. Okay, TM. Okay, after that, we are going to the MAC layer. MAC layer means Medium Access Control. This layer can decide how to scheduling, how to transmit our information. So the MAC layer can decide QoS because the MAC layer can decide how to transmit information. Okay, after MAC layer, we're going to the physical layer. Okay, physical layer you can think just like a road. Okay, this road is connect to the next station. The next station here means E0B. Okay, so from here, from APP to physical layer, our information, our data, just like a pack procedure. Okay, and going to the next station, going to the E0B, first the E0B need to unpack because E0B should decode what you transmit. So the protocol you can think just like different languages. Okay, languages. After unpack, okay, you should prepare the data transmit to the next station. The next station is SGW, so the inner B need to pack again. But we know this interface is not a radio interface, right? This interface is S1 interface. S1 interface is a fixed interface, right? So the protocol cannot use the same like a radio interface. So it need to use a new protocol. For example, like a GTPU, like a UDP, like IP layer. So this protocol is very similar like OSI 7 layers protocol. Okay. After that, the same, the SGW will unpack, and then SGW also need to pack again and send to the data to the next station. I think here the next station is well. Next station is PGW, right? The SGW will send to PGW. And then PGW will send your data to internet. Because the PGW is connected to the internet, right? So after send to internet, your data will transmit finish. Okay, so this is data stream. For signal stream is very similar, but the protocol is a little different. For example, here there has a NAS. NAS means non-access stratum. This protocol is only transmit to the MME. So also we can also understand only MME can decode NAS. So how to send NAS to the MME? It need RC, right? RC is a radio resource control. RC you can think it is only transmit signal in access network. Okay, so this is NAS, this is AS. And after that, PDCP, RLC, MAC, physical, this is the same like before. Okay, same like before. And then the UE send the signaling to the inner B, and the inner B also unpack the signaling, and then the inner B will pack again. We'll use a new protocol and pack again, such as S1AP, SDP, IP layer. Okay, because now we need to send a signaling through S1 interface to MME, so we are using S1 AP. If this inner B want to send signaling through X2 interface to another inner B, it need to use X2 AP. So this you can think this protocol just like a guide, just to show you which way you want to transmit. Okay, here is AP. AP means application, so we can think this is a application layer. And SDP is only used for signal transmit protocol in LTE system, right? This protocol named Stream Control Transmission Protocol. Okay, after that, send to the core network, and the core network unpack. The core network MME will understand what you want to transmit signaling. Okay, so this is the LT and L and SAE protocol structure. And last, we will talk about LT frame structure. Okay, frame. First, you should understand what's the meaning of frame. Frame, actually, this is the time concept. You know, in 2G and 3G, we also have a frame, but the duration of the frame, they are different. For example, in 2G, in GSM system, one frame include 8 time slot, right? It totally is 4.615 millisecond. And in 3G, one frame is 10 milliseconds, include 15 time slot. Okay, let's see the LT. And LT, we can see one frame is 10 milliseconds. Okay, one frame is 10 milliseconds. And then one frame will divide into 10 parts. So that means each part is 1 millisecond, right? 1 millisecond, we named one subframe. Okay, one subframe. And one subframe we also divide into 2 parts, and each part is 0.5 millisecond. So each part named is 1 time slot. Okay, one time slot. So we can see here, every 10 millisecond radio frame is divided into 10 subframes. So each subframe 1 millisecond. And then every subframe has 2 time slots, and each of which is 0.5 millisecond, right? So each one is 0.5 millisecond. So in here you should understand, in LTE frame, one frame is 10 millisecond, and each frame include 10 subframe. Okay, so each subframe is 1 millisecond, and each subframe include 2 time slot, and each time slot is 0.5 millisecond. So here you should understand frame, subframe, and time slot, and what's the relation between this. Okay, the next concept is TS. TS, here TS is not means time slot. This TS means basic time unit. Okay, basic time unit. So this is the time unit in LT. It's similar like our time unit in our life. For example, the hour, minute, second, right? This is our time unit. But in LT has his time unit. So what is 1 TS? 1 TS is equal to 1 divide 15,000 multiplied 2048. And here 15,000 means 15k hertz. Okay, this means 15k hertz. And 2048 means 2048 samples. Okay, samples. If you want to know the details of 15k hertz and 2048 samples, you can read our document in details. Okay, but here you should know 1 T is like this to calculate. Okay, and the unit is second. Okay, so that means 1 T is equal to 1 divide 15,000 multiplied 2048 seconds. So now we can know the relation between TS and the second. If we know this, we can understand why one radio frame can represent 10 milliseconds, also can represent 307200 TS. Because 1 second, because 1 TS is this second, right? So if you change, if 15000 multiplying 2048 TS, that means 1 second, right? 1 second. So that means 1 second include 15,000 multiplied 2048 TS, right? But now this is not 1 second. This is 10 milliseconds. So this value we need what? We need to divide by 100, right? If this value divided by 100 and the result, it will be 307200 TS. Yeah, you can try to calculate. Okay, if we know one frame is 307200 TS, what about one subframe? One subframe, of course, is 3072, is 3072, right? TS. What about the one time slot? One time slot just like this value divided by 2, right? So the result is 15360 TS. Okay, so from here we can know the relation between TS and seconds. So next time we can use the millisecond. Yeah, the millisecond represent our frame, subframe, and time slot. We can also use the TS represent our frame, subframe, and time slot. Okay, so this is the LT frame structure. Okay, so this is the end of this course. Thanks for your learning.